Oh, we ought to learn that. Come on, darling, let's learn it. It's a party. Let's celebrate.
If you love listening to this show, please consider giving a rating and a review on Amazon Alexa or wherever you listen. We want to continue bringing you this amazing content, and part of our ability to do that means that we need a big audience. Now, it may not seem like much, but rating and reviewing the show will help more people find us, just like how you found this show. Simply on any podcast platform, search for a show, scroll down to the bottom, and push 5 stars. It's that easy. Thanks for supporting the show. Today, I'm joined by Bob Baxley, who is a CTO at Bastille Networks that provides threat detection and security for the Internet of Things. Bob, thanks for joining today.
Hey, Scott. Thanks for having me.
So first and foremost, you're a scholar and a researcher, having published over 100 peer-reviewed publications and patents. And a lot of your work was done at the Software-Defined Radio Lab at Georgia Tech. Can you tell us a little bit about kind of your specialty and the areas that you're most passionate about?
Sure. So my academic background is in signal processing, mostly related to RF signals and RF systems. So I did my PhD in optimizing LTE communication systems, and then I went on and did a bunch of research around cognitive radio systems. The idea in cognitive radio is you want to be able to build radio systems that can adapt to their environment. So spectrum's a precious resource, and so you have areas where there's scarce spectrum because there's a whole bunch of users. Cognitive radio, the idea there is that you've got autonomous radios that can reason about where spectrum is available and then operate in that spectrum in an agile way so they don't affect the other users in the spectrum. So we did some neat things. One of the more neat projects was a project called RadioBot, where we put software-defined radios on a number of mobile robots. And the idea is not only would the radios have agility in spectrum, but they also have spatial agility. So the robots could reason about where to spatially move to achieve their spectrum objective. And the objective isn't always just communication. Sometimes it's sensing, like radar sensing. Sometimes it's passive sensing, like sensing the other signals in the environment. And sometimes it's even imaging. So RF tomography is a mechanism where you can image the spatial loss field in an environment. That is where all the shadowing objects are, like walls and these sorts of things. And by doing that, you can understand how your RF propagation is going to propagate across the network. So most of my research when I was at Georgia Tech was putting all those pieces together to create agile radios that could reason across these different modalities to optimize whatever they're trying to do, sensing or communication.
Well, now that you explained that, I think it makes a lot more sense in terms of why some of the DoD and its partners have worked with the lab to explore some of these possibilities, especially in difficult environments where, like I said, it's not just about communication and signaling, but also sensing as well as other kind of multimodal aspects as well that leverages the RF aspect. Now, radio frequency as a kind of a general domain has been around for, of course, many decades. But what's really interesting is this, rise and density and ubiquity of the Internet of Things. And to your point, you were experimenting with mobile robots. Now, well, technically, we have these devices in the form of smartphones that we carry, but now we also have these edge devices as well. Some that are static, that are not moving, but in other cases, they're autonomous and they're also actually moving as well. How do this new environment open up vulnerabilities in terms of transmitting, data and packets over RF? And, what's a kind of, potential danger that it poses to an entire security infrastructure for an enterprise?
Sure. So there's a few different elements to that. One big one is just by having new radios, these IoT radios, a bunch of them operate on new and even proprietary protocols. So it's like the wired internet in the 90s, when there was a proliferation of protocols, there was passwords being passed around in clear text, And it wasn't until you had network security companies like ISS in the very early days scanning this network traffic to understand that these various protocols had these vulnerabilities, and that it was possible for a bad actor to inject bad packets or malformed packets and take down different pieces of infrastructure. So we're seeing that repeat itself in IoT, because these new protocols that drive IoT communications over radio aren't that robust.
Mm-hmm.
Protocols like Wi-Fi are very robust, Bluetooth very robust. They've been around a long time. Lots of eyes have been on the protocol trying to tear it apart. But newer protocols like LoRa and Sigfox and these IoT protocols that are hitting the long-range, low data rate kind of sweet spot, we're seeing lots of vulnerabilities being disclosed by security researchers there. So some of those vulnerabilities are just inherent in the protocol, like encryptions, that there's a corner case that wasn't considered. But other vulnerabilities are manufacturers who are developing these SoCs that run the protocol decoders that do the communications, haven't considered corner cases. So lots of attacks have been disclosed in the literature where an attacker changes, for instance, the length field in a packet. And they make the length field some unreasonable value. And that ends up crashing the end device, which could take down a big piece of infrastructure if you're depending on these IoT systems. Other researchers have even shown that you can inject malformed packets in such a way that you get remote code execution on the end device. So you can imagine if you have IoT protocols or protocols running your data center, if someone can get code on that device, and that device is on your core network, they're now on your core network. So this becomes a jumping off point. So it really becomes part of your attack surface that you have to consider. And one of the ways to figure all that out is to have eyes on these devices when they get deployed in your space. You want to be able to monitor the network traffic that goes over these RF interfaces.
Yeah, I think I really like the way you've kind of laid out the landscape. Is that we do have a lot of different players coming into place, and then with their proprietary standards and protocols. And although many of the pioneers are from legacy, standards and protocols, in new contexts, and specifically to your point, these kind of corner scenarios, things that are more kind of outliers, less common, that hasn't been thought through, hasn't been addressed either at the standard protocol level or at the SoC chip level. Really, it just shows you kind of the nascent stage until we get to a point of either merge or a common set of standards and protocol. Most likely that's not going to happen anytime soon. We're going to have a lot of these issues. And the last point you made, I absolutely agree with you, is that no matter how secure an enterprise is, their strongest point is still subject to the weakest point, which is that small IoT device that that was really insignificant, but in fact that's a gateway to the rest of the world. Can you talk a little bit about your proprietary sensor arrays and analytics that are continuously scanning the airspace and then detecting for the wireless emitters, as well as the digitally demodulating those signals and identifying the protocols and the unique devices? Sure.
So a few things about that. So in my work with Georgia Tech, where I was doing both NSF type contracts, but also working for organizations like DARPA, one thing that comes up in the DoD is you want to be able to understand what kind of RF signals are in a space or out in the battlefield. And so to do that, they have highly trained experts that are looking at kind of raw readings from spectrum analyzers to understand spectrum analyzer devices, to understand what emitters are in a space. So the idea at Bastille was we would take that kind of expertise that's in an expert's head and put it into a system that's automated so that you don't have to have advanced training in how RF signals work in order to understand what's going on in a facility. So we built a software-defined radio detection system. And how that works is we deploy sensors that look like Wi-Fi access points. They're a little bit bigger than Wi-Fi access points. And inside the sensor are two independently tunable software-defined radios. Now, what does software-defined radio mean? In your phone, there's a LTE chip, for instance, and a Wi-Fi chip and a Bluetooth chip. And if you want to upgrade to 5G, you need a new chip. because all of the RF modulation, demodulation, all the communication smarts happens in hardware. That's the cheapest way to go, and it's low power, but it means that you don't have any flexibility. So as new protocols come out, you're buying a new phone. That's not the best scenario for scanning technology like we've built, because you wouldn't want to have to reinstall sensors every 6 months as protocols evolve and new protocols come out. So the way to get around that is you define all the demodulation in software, hence software-defined radio. And so that's what we've done. We've got a big FPGA, which is a type of processor, that lets us do parallel decoding of hundreds of channels at a time. And so we're demodulating things like Bluetooth and Wi-Fi and cellular signals. We don't actually see the payloads. We don't see the encrypted payloads. We don't see anything above layer 2 generally. But we are able to see things like MAC addresses and understand devices as distinct from each other. And so the net result of all of that is our customers are able to see a dot on their floor plan map for each emitter in their facility. And then we have a DVR view where they can go back and forward or back in time and see where a particular device was in the past. They can also click through our analytics and see what types of packets the device was transmitting over time. Yeah.
So this makes a lot of sense, and certainly given a, let's say, physical facility, whether it's a office building or, let's say, a utility or oil and gas, where things are somewhat fixed, you can afford to have these kind of sensor arrays with software-defined radio, embedded there with a connected kind of a electrical outlet source, right?
Right.
But in terrains where things are more dynamic, let's say in military contexts, where maybe power sources is problematic, because again, I'm thinking that your approach is a little bit more power intensive than the hardware approach, like you explained before. The other aspect is that, when we think about kind of new threats, there is also autonomous threat. So in the case of, let's say, oil and gas, there's been attacks using drones, and we're talking really small, tiny drones that are carrying some sort of payload that's causing explosions or whatnot. In those kind of, more dynamic and moving autonomous kind of environment, how does your system work, and how can it be fitted to support those missions?
Sure. So there's a couple aspects of that. The first tenet of securing your network is understanding the interfaces into your network. So the first thing you want to do is be able to have a technology like ours that can scan and make sure that you don't have unknown interfaces, unmanaged interfaces into your network. For instance, we saw at one of our deployments, there was a chiller in a data center, and the customer was administering the chiller, the air conditioning unit, via the Ethernet interface. But little did they know the chiller also had a Zigbee interface that they never used, that was default on and unencrypted and ready to accept someone to control that chiller. So the first thing you want to do to avoid being attacked is just do network scanning, and do that continuously, so as you bring in new infrastructure, you don't get caught with your pants down. The dynamic threat is interesting. So there was actually a really neat demonstration by a research group where they showed something called an IoT worm. And again, it was a Zigbee attack. They showed they could fly a drone with a Zigbee radio, a small little Zigbee radio, near a building, and they could compromise all the Philips Hue light bulbs. And since Zigbee is a mesh network protocol, they were able to put their payload on one of the light bulbs and then have that payload do a firmware update for any adjacent light bulb that was in the transmission radius of that original light bulb. And then it would self-propagate for as long as it could hear new light bulbs. So that, as you said, that can happen in oil and gas, and here's a really tangible example of it happening, across like a building. So the way we would see that is, again, we would tell the customer, look, you've got these Zigbee interfaces. They may be vulnerable. You want to make sure you secure them. And when somebody tries to push a new firmware update to them, we would see that sort of packets and those sort of traffic. And so you get an alert and you understand that maybe you've been compromised.
Fascinating, really fascinating. And there's so many use cases for such a thing. I want to explore just a little bit around your core IP, in the sense of, the really underlying patents as well as the trade secrets that you can share, of course, and how that is different and defensible relative to similar competitors in that RF security space.
Sure, great question. So I think we're up to 22 or so patents so far. So we've patented lots of aspects of how you use software-defined radios to find signals, to demodulate signals in parallel. I think one of the more recent patents was around how you infer Bluetooth and Bluetooth low energy connections. So it's not straightforward to just see Bluetooth traffic and then understand that this device is connected to that device. A lot of that connectivity information happens behind encryption. So one of the neat things that we're able to do, well, Bluetooth is a frequency hopping protocol. That means when your Fitbit pairs with your phone, every 600 microseconds, they're jumping from one channel to another. There's 79 channels that are jumping between in the 2.4 gigahertz band. Every Bluetooth chip I'm aware of is only looking at one channel at a time. So your phone and your watch are jumping channels synchronously. But if you wanted to see all the devices, you'd want to see all 79 channels. And so that's what we've done, is we actually have a 79 parallel instantiations of a Bluetooth decoder that are listening to all the channels. And by doing that, we can run other analytics to infer that these two devices, for instance, are hopping together, so they must be connected. We can make higher level inferences that are valuable to our customer. For instance, some customers have policies where a disconnected Bluetooth device is allowed in a certain restricted area, say. But as soon as that Bluetooth device pairs with another device, that may be indicative of data exfiltration. And so they would have an alert around that connection, and that's something that we flag as the metadata, so you could easily write an alert if that's of concern to you.
Now, there's so much that you guys can do. At some point, it becomes a kind of an organizational policy issue as well. I think you mentioned the importance of why enterprises need to implement and enforce nuanced electronic device policies. Can you elaborate on that? Sure.
So I think there's lots of enterprises, especially federal enterprises, where they're very concerned about RF data exfiltration. So lots of those places have blanket policies where no devices are allowed that emit RF. But once you start digging into that, you realize that, well, it's no longer possible to buy a hearing aid, for instance, that doesn't have RF enabled. And you can't, you're not going to exclude everyone who needs a hearing aid. So then it becomes more nuanced. Now, I want to restrict almost all devices, but I do want to whitelist medical devices, glucose monitors, hearing aids, these sorts of devices. So that's where you start getting into this nuance, where this device is allowed. It's only allowed under these certain conditions. Say it's not connected, for instance. It's not connected to its phone. Another set of nuanced policy is we have customers who want to make sure their devices stay on a certain channel, so a certain frequency, because they know that there's interference in adjacent frequencies. So what can happen is if they push out a firmware update to all their devices, maybe they lose that setting and they start using the wrong frequency, and they get subtle but noticeable performance degradations in whatever system is relying on this communication link. So we help them do that kind of monitoring as well.
Now, you mentioned that you guys are able to see kind of was it above level 2, kind of the MAC address, those sort of things. Are you able to analyze patterns so that without actually having specific rules that to identify that this is a earbud versus a headset versus something else, and the kinds of behavior, the kinds of packets, and the frequency to be able to dynamically detect anomalies or outliers or just strange behavior?
Yes. So yes to the first. That's another patent we have is, we call it traffic fingerprinting. By understanding that this sort of traffic pattern has these sorts of latencies and these sort of packet sizes, we can classify it as one group or another. Anomalies is a little trickier, because every time we do a deployment, we see new and different kind of modes of operation for RF devices. So we do let our customers write rules, but kind of blue sky anomaly detection is a little bit more difficult.
Of course, absolutely. Well, we're almost out of time. If you could share, whether it's from your research or from practical commercialization projects or products that have maybe failed, what kind of lessons learned that you can share with others?
Well, a big lesson learned at Bastille is that hardware is hard, which I think most people know. But pulling together hardware, building real devices that work and work all the time robustly across different temperature ranges and different operating conditions is very, very hard.
Mm-hmm.
I think, that's good when you're in a company if you figure it out, and we figured it out now, because it makes it, it's a big differentiator. Not anyone can just go build the hardware we've built. But I would, if you're going to go start a hardware company, make sure that you're prepared and you've got the right people that know how to work with contract manufacturers and work with the FCC and UL and all these different certifying organizations to make sure your hardware can operate properly.
A lot of wisdom, and I'm sure hours of frustration and the iterations have gone into that. So today I've been joined by Bob Baxley, who is the CTO at Bastille Networks. Thanks for joining today, Bob.
Okay, thanks, Scott.
If you've enjoyed this episode, take a moment to rate our show on any podcast platform that you listen to. Scroll down to the bottom and push 5 stars. It's that easy. And as always, thanks for listening.